Hey, Physics 20s, it's Mr. Jukely again. We have our very, very last lesson of Unit 5. It's Lesson 9, and it's all about orbital motion. So let's jump right in. Let's check out orbital motion. So first off, trying to figure out and trying to explain orbital motion. Newton came up with a great analogy for this. So let's say that you are, standing on top of a really tall building. So here you are, standing on top of a tall building, and you wanted to throw a rock off of this tall building. You threw it horizontally off this building. Well, you know what's going to happen, right? It's going to go into nice parabolic motion, and it's going to hit the ground. Cool. What would happen if you threw it a little bit harder? Right, so have a little bit bigger of an initial speed. Well, it's still going to go into that nice parabolic motion, and eventually going to hit the ground. And then a little bit harder, I think you might see where we're getting for this. It's going to go into that parabolic motion and hit the ground a little bit further and further. Let's zoom out a tiny bit here. So let me just erase all of this stuff. And now nobody can really throw this fast. So let's pretend that we've got a cannon instead. So here's the Earth. Here's that really tall building or that tall mountain. And we've got a cannon. And now we're launching this. Like this is a really, really, really powerful cannon. So you launch it, and it might make that same parabolic motion. You launch a little bit faster, might make that same parabolic motion. Do you see what's starting to happen here? Let's clear out those last two lines. There's one of them, almost. Okay, where is it? Why is it not going away? Almost. There we go. If we threw it fast enough, it would fall towards the Earth, but that falling would eventually start to match the curvature of the Earth, and it would never actually hit the Earth. So if we've got enough of this speed, or I guess in this case technically velocity, the way that we've got it drawn there, there is constantly an acceleration towards the center of the Earth. And if we've got, again, enough speed, we can kind of overcome it actually hitting the Earth. And this is the idea of orbital motion. So instead of a cannonball, picture the moon. Oh, that is the worst moon. Okay, that is a terrible moon. But, okay, so picture a moon. Picture a satellite. I'm not sure this is going to be much better. I mean, it can't really be much worse. Picture a satellite, same sort of idea. So it's continually falling towards the Earth, but it's got enough speed to prevent it actually ever hitting the Earth. Cool, so let's check this out, and let's see if we can figure out and build a formula with orbital speed. So we know it's got this velocity. We know it's got an acceleration towards the center of the Earth. What's causing it to fall towards the Earth constantly? Right? So if we go back to here, we say Fc. Remember, that's just the net force. Fc is equal to, well, what's the force that's attracting that satellite to the Earth? Oh, it's our force of gravity. Nice. Okay. So Fc is m times ac, because remember, it's just net force. So it's the same formula. Mass times acceleration, but special for circles. And then Fg, well, let's see here. We could probably use m times g, right? Absolutely, we could have a look at that. The big problem is if it's not on the surface of the Earth, it is not 9.81. So we might need to expand on what g is a little bit here. Okay, and if we're looking for orbital speed, we can also probably expand on ac, because we know that ac is realistically v squared divided by r. So let's plug some stuff in. M v squared over r is equal to m times g. That's my gravitational field strength. Okay, so that's gravitational constant times the mass of the thing that's making the gravitational field. So I'll put that as a capital M to differentiate it a little bit. Here's our capital M. And then divided by r squared. Cool, some things cancel off now, I think, right? Definitely. So some of these masses cancel off. So what mass is actually in circular motion here? The Earth that's going in circular motion is the satellite. So it's the mass of the satellite. And then what mass are we talking about here? That's the mass in something else's gravitational field, so this mass. So that means these two masses are actually going to cancel out. That's, again, the mass of the satellite that is canceling out. The mass of, I'm pretending that this is the Earth. The mass of the Earth is something that's left behind. Cool. The radius, one of those radius cancel out. Okay, so let's see here. I got v squared is equal to g times the mass of the Earth divided by the radius. Now, one thing that I will note is that's my orbital radius that we're dealing there. Cool. So, long story short, there's a couple different ways that you could deal with this. One, we could start with FC is equal to FG, and we could expand from there. Or even in our second step, right? Because we said M times AC is equal to M times G. We saw the masses of the actual satellite canceled, so we could also say that the acceleration is the acceleration due to gravity or the gravitational field strength at that point. Again, the big key with this is it's not 9.81. So two different ways to look at the same idea. We could talk about forces, or we could talk about this satellite being in free fall where the acceleration is the gravitational field strength, but not 9.81 meters per second squared or newtons per kilogram because it's way up there in space. Cool. Okay. Let's see, if we were looking for orbital period, it's essentially the same thing. Any ideas what we would do? So we could say FC is equal to FG. So M times AC is equal to M times G. Again, we see those masses cancel. That is the mass of the satellite that is canceling. So let's see, I got AC is equal to G. So in other words, again, it's in free fall, except I think for AC this time, I might use 4 pi squared R over t squared and say that this is going to be equal to, okay, so my gravitational field, that's G times the mass of the thing that's making it. So again, that's the big mass over here, and then divided by R squared. And you'll notice in this case, R doesn't actually cancel, right? In the last one, R canceled. In this one, R does not cancel. If you wanted to rearrange and solve for R, you'd actually end up with R cubed before anything else. Cool. So two different ways, essentially the same thing. Starts with FC is equal to FG. We, from that, get that it's in free fall. AC is equal to our gravitational field strength. And then we expand to build whichever formula we need. Okay, let's think about this for 2 seconds. Which of these two satellites would need to be going faster? Which of the two satellites would need to be going faster? Put on pause and think about that. Go ahead and do that right now. All right, so I hope you had an opportunity to think about that. Let's go see if we can go through and see if we can prove which one must be going faster. So we got, I'm going to call this one satellite 1, and I'm going to call that radius 1. I'm going to call this one satellite 2, center to center. I'm going to call that radius 2. All right, so 1 or 2, which one do we think is going faster? Well, I'm not going to do specific math for each of those, but what I do want to do is I want to look at, so obviously I'm looking at speed, and I want to look at the relationship between speed and radius. So again, I'm going to start with FC is equal to FG, our usual kind of thing. So net force is the sum of all forces. M times AC is equal to M times G. And again, the mass of the satellite cancels out. So the satellite, I don't even care about the mass. Mass of the Earth I definitely need. But let's see, I'm going to expand on this. AC is V squared divided by R, and G, gravitational field strength, is gravitational constant times the mass of the Earth divided by the radius squared. Keeping in mind that's the orbital radius. So let's see, I'm going to cancel those ones out. And let's see, it looks like I got V squared is equal to G M over R. Now if I wanted to look at just V squared, so I'd take the square root of both sides. Now I can look at the relationship. V has an inverse relationship with the square root of R. So let's think about what that means for a second. As the radius gets bigger, what happens to the speed? So let's say that we multiply the radius by, let's get a different color here. Say that we multiply it by 25. That's quite a bit bigger of a radius. What would I have to do to the speed? We'd have to divide by 25 squared, or the square root of 25, or divide by 5. So as the radius increases, so when the radius increases, the velocity or the speed decreases. So in other words, the one that's closer has to be going faster, the one that's further away is going slower. Cool. All right, so same sort of thing. It's an inverse square root relationship. You could also think about it as having to overcome gravity, because satellite 1 would have a larger force of gravity than satellite 2, so it would have to going faster to overcome that force of gravity or that acceleration. Some of the satellites that are going close to Earth can be going like ridiculously fast, 7 to 8 kilometers per second, or 28,000 kilometers per hour. That's pretty crazy. That's pretty fast. All right, so let's check out a quick example here. Determine the orbital speed of a satellite that is 750 kilometers above the surface of the Earth. This really doesn't look like it gives us a bunch of information, but remember, a data sheet gives us a ton of good stuff. Tons of good stuff. So first thing that I want to do is I'd want to figure out the orbital distance, or the orbital radius, r. So here's my satellite. Here's what's given to us. We know that this is 750 kilometers. I don't really like kilometers though, so I might go ahead and change that into meters. 750,000 meters. So that's the distance above. I know that the radius of the Earth, and this is just off of our data sheet, is 6.37 times 10 to the power of 6 meters. I'd better double check that one. Good, 6.37 times 10 to the power of 6 meters. And then my orbital radius, well, that's from the center of the Earth all the way out, so RO, all the way out to where the satellite is. So if I wanted my orbital radius, RO, that's just going to be the radius of the Earth plus the distance above the surface of the Earth. So go ahead and plug that in. 750,000 meters plus 6.37 times 10 to the power of 6 meters. Let's see, I end up with 7.12 times 10 to the power of 6 meters. Cool, okay, so we've got now our orbital radius. That's going to be kind of important for this one. Now I want to use the ideas of uniform circular motion, and I know that Kepler said, hey, these are more like ellipses, but it's pretty darn good estimates if we're using circular motion. So I want to go through and I'm going to say FC is equal to FG. So start off with our, what is causing that satellite to stay in circular motion? So what is my net force, in other words? My net force is mass times acceleration. It's a special acceleration. It's AC. And then my force of gravity, well, that's just m times g. Again, the mass of the satellite. Satellite is the mass that cancels out. Let's see, I want to expand on AC. I know that AC is the same thing as v squared divided by r. So I'm just going to put that on my left side of the equation. And I know that my G, or my gravitational field strength, is G times the mass, in this case of the Earth, divided by the orbital radius. I should put that as orbital radius as well. So yeah, we'll plug that one in. G times the mass of the Earth divided by the orbital radius squared. We see one of those squares canceled with that. And let's see, we are looking for the speed. So speed must be equal to G times the mass of the Earth divided by the orbital radius, and then I want to take the square root of that whole thing. I hope everybody's okay with the rearranging. And all we got to do from here is plug in some numbers. So 6.67 times 10 to the negative. I better double check that one as well. Good. 10 to the negative 11 newtons meters squared over kilograms squared times the mass of the Earth, 5.98 times 10 to the power of 24 kilograms. And then we want to divide that whole thing by our orbital radius. We just figured that out. There it is, 7.12 times 10 to the power of 6 meters. Go ahead and plug that into your calculator. I will do the same. I'm ending up with 7.48 times 10 to the power of 3 meters per second. I guess I could scroll down a little bit there, which is pretty crazy fast, right? Like that satellite, 7.5 kilometers every second. Wow. Wow. Pretty fast. So this is the idea of satellite and satellite motion. Next time you're out there in a dark night, check out some satellites. I saw a whole bunch of them over the long weekend. There was moonless, it was dark, it was clear. You can see tons of them. They look like stars, but they're flying across the sky. Okay, that's some space for me to work. So we kind of already talked about this. Lots of people think you're in zero gravity when you're, in a spaceship, like this astronaut right here. Looks like she's in zero gravity. Is she really in zero gravity? Not really what she is she's in free fall, or in other words, her normal force is equal to 0 because she's falling at the exact same rate as her spaceship and everything else around her. So this is what we mean by weightless. It's your apparent weight. There's obviously still gravity acting on her. It is pulling her towards the Earth. She's just moving really, really, really fast to the side and never actually contacting the Earth. So there's a couple cool videos of this that you can check out. There is Chris Hadfield. I guess that's a capital H there. Chris Hadfield. You can check out his Space Oddity video. You can check out Crying in Space. You can check out Drinking in Space. There's a couple other Chris Hadfield. Oh, Wringing Out a Towel is pretty cool. But Chris Hadfield is Canadian astronaut who got pretty famous by doing a bunch of experiments and music videos and stuff in space. So again, Chris Hadfield's Space Odyssey is one thing. Crying in Space. Wringing Out a Towel. I think there's a W in front of that. Maybe not. Wringing Out Towel and Drinking in Space are all pretty cool videos from Chris Hadfield. We've also got, so see if you can think about this one. So here's a candle flame here on Earth. Here it is in microgravity, essentially in orbit. Any ideas why? Right, so why one of them would burn like we'd normally see on Earth, but in zero gravity or zero apparent weight at least? We got this weird sort of thing. I'll let you think about that one. Oh yeah, and there's the drinking coffee in orbit. Low gravity experiments. So they've to train people for this, and there's no, like in Ender's Game, there's no like battle room or anything like that. So essentially what they have is they have airplanes. One of them is called the Vomit Comet, which is pretty hilarious. And essentially what they do is they accelerate upwards like crazy. The person feels way heavier here. Accelerate upwards, they go over the top, and then the plane actually starts to fall at the same rate that the gravity would be pulling the people down at. So in this particular thing right here, the people are in the plane, but they're kind of like floating in the plane. It's essentially weightless, right? Or apparent weightless, I guess is a better way to put it. So holy mackerel, that is a huge link. I didn't realize quite how big that was. Just look up Vomit Comet on the internet and you will find that video. It's pretty cool. I'd love to do that one day. That'd be pretty cool. Big Bang, I don't even remember which one this is, and to be honest, I don't like Big Bang that much. But anyways, oh, I remember what this one is. Space Training with Harold. So if you want to look that one up, I think it's Harold. You can absolutely check that out. Astronaut training. Okay, last thing to really talk about here is geosynchronous orbit. So geosynchronous orbit, well, geo means Earth, synchronous means synchronized or the same. So it is synced up with Earth's rotation, in other words. Long story short, it's got the same period of rotation as the Earth. What's the Earth's period of rotation? It's 1 day, which is 24 hours, which I don't remember off the top of my head how many seconds it is, but we sure could figure that out. So again, a geosynchronous orbit is rotating at the same rate that the sky is rotating, or sorry, that the Earth is rotating. So it takes the Earth 1 day to get from there to there. Guess how long it's going to take the satellite to get from there to there? Again, 1 day. That being said, what has to move a lot quicker? Well, it's the satellite rather than the person on the surface of the Earth because they've got way further to go in that same amount of time. Now, if we were to look at this up in the sky, it wouldn't look like much because that satellite is staying at a fixed location. Right? So it's always at that same location above the surface of the Earth. Any ideas why this is important? Pretty much everything communications this is important for, right? So for satellite communication. So just imagine with like your satellite dish or whatever, if this satellite was constantly moving across the sky, you would have to constantly orient your satellite in order to communicate with the satellite dish, in order to communicate with the actual satellite, and that would be an annoying pain in the butt. But if it's in one location, so it's not actually moving, and it's just in, or appears not to be moving, I should say, at one point in the sky, you can hook your satellite dish up once, or your cell phone tower up once, and it's going to stay that way. Right? It's going to be awesome. It's going to be perfect. So let's just think about this. How would I determine the orbital radius of a geosynchronous satellite? How could we do that? If you're thinking to yourself, the same thing that we're thinking before, FC is equal to FG, you are spot on, right? So we expand on that, MAC is equal to M times G. Remember, the mass of the satellite is the thing that cancels. Now it's our AC that's a little bit different here. So 4 pi squared R over T squared is what I want to use for AC. And then gravitational field is just, again, not 9.81 because it's not on the surface of the Earth. But we can figure it out, assuming we know, the mass of the Earth and the period. Question is, period is missing, so all we really got to do with this, well, one is we want to rearrange and solve for the orbital radius, and then two, we'd want to go ahead and I'll probably figure out, maybe in the other order even, figure out the period. So first and foremost, period's fairly straightforward. Right? Period's not too bad. 24 hours, it's 1 day, there's 3,600 seconds in an hour, so we can figure this out. This is done a little bit differently, but we see the same thing. The mass of the satellite actually cancels, so who cares about the mass of the satellite? When we go through and rearrange, we have to use a cubed root for this. Push math on your calculator, so that's right. Let's see how to describe that, and I don't have my calculator open. It's 2 buttons below your second function on your standard TI-83s and 84s. But anyways, we plug numbers in, 4.23 times 10 to the power of 7 meters, or about 42,000 kilometers from the center of the Earth. Cool. Anyways, that is our last lesson on orbital motion. Good work, everybody. Our last lesson on Unit 5. Good work, everybody. I don't think I have much else to say, so I'll just say bye for now, and we'll talk to you again soon. Bye, Physics 20s.